Okay, we've looked at the magnetic field for a small piece of a current, a little differential length ds of a wire. And if we take that and extend that and look at like a loop of wire, one loop of wire with current flowing through it, the magnetic field on the axis of that loop, at the center of the loop, is given by mu naught, the permeability of free space, times the current divided by 2 times the radius of that loop. If you look at a magnetic dipole, which is a loop of current, and you're looking at that some distance from the current, then the magnetic field on the axis is equal to mu naught over 4 pi times 2 times the vector mu, the magnetic moment, which you'll do the current times the cross-sectional area, divided by z cubed. Now, let's look at the inside of a coil of wire. There's a little bit of a teaser or a spoiler. We're going to look at this and find this a very useful thing to do in much the same way that looking at the electric field between 2 gigantic plates was a good thing to do. Now, we have, at this point, Ampere's law that tells us that if I follow a closed path, the integral of B dot dl, where dl is the differential part of that path and B is the magnetic field strength, around that closed path is equal to mu naught times the enclosed current. We can make this useful here by carefully choosing our closed path and the direction we're traveling. So let us say that we've got some current passing through that wire, and I want to choose a path like so. Now, here's why that's cool and sneaky. If I take this and I track this in, say, this direction, then first off, I'm taking that integral. Let's say path 1, path 2, path 3, and path 4. So, that integral actually becomes the integral over bit 1 plus the integral over bit segment 2 plus the integral over segment 3 plus the integral over segment 4. Now, here's the next sneaky bit, or actually the first sneaky bit that we're going to do. Let's go ahead and say that the far side of my loop is infinitely far away. If the far side of my loop is infinitely far away, then the integral of B dot dl along that path, if I'm far enough away so that B is basically 0, that means that section is 0. Now, if I'm taking the magnetic field and the dot product with that, with the differential step I'm taking in the direction of my path, well, then the magnetic field, which through this case will be the sum of the magnetic field of each loop. We already know for the magnetic field of one loop, that's going to be perpendicular to the surface. So, because these dot products will give me a result of 0 if I'm doing something that, if I'm taking that, the dot product of two perpendicular vectors, then, whoops, yep, those two segments will also go to 0 because cosine of 90 degrees is equal to 0. So I'm left with B dot dl on segment 4, the integral, those aren't closed paths. Together they are one closed path. So we've got the integral of B dot dl over segment 4, and that's equal to mu naught times the enclosed current. Now, if I'm going in this direction, at every point as I move along segment 4, dl is perpendicular to the surface. At every point for each one of these individual little loops, the magnetic field as I pass through that loop is perpendicular to the surface. So B dot dl is just equal to the integral of B dl, which is mu naught times I. Now, the magnetic field, if I'm deep enough in, okay, right here I'm making one approximation I did not tell you about yet. This is it. This is the, please disregard my poor artistic skills, and assume that I drew a really huge solenoid, so that we don't have to worry about any fringing effects because we're kind of close to the end. If this is part of a huge solenoid, then the magnetic field, which depends upon, oh, here's the loop that I'm in, and the two loops closest to me, and the two loops closest to that, and so on, out for a great distance. If I don't get anywhere close to the end here, then that's going to be constant. So I'll have the integral of b times, that comes out of the integral of dl, which just becomes the length of this line, is equal to mu naught times the enclosed current. Now, I have something here that looks like it should be a problem. I have a case here where this this result, as I'm looking at it right here, depends upon L, the length of that path. But the length of that path is arbitrary. It's made up. If it turns out that it actually becomes important in the answer, we're kind of stuck. However, if I look at this, this is the enclosed current. Now, I can rewrite the enclosed current like so. The magnetic field times the length of that arbitrary path, that arbitrary length, is equal to mu naught. Now what's the enclosed current? Well, each time it grabs one of those loops, it grabs the current I. So it's the base current I times the number of loops I've got, which is the number of loops per unit length times the length of my arbitrary figure that I drew. And these two arbitrary lengths cancel out, which is wonderful. It means that they really are arbitrary. And the magnetic field inside a solenoid is equal to mu naught times the number of loops times the current divided by the length, which I could also write as mu naught times the number of loops per unit length times the current. Both of those are correct. And again, I've just got the downside is that, this is finding the magnitude. We'll have to find the direction again using the right-hand rule. But hopefully we've done that a couple of times by now, so we can see, track the direction of the magnetic field by the direction of the magnetic field caused by each loop. Since each loop is stacking on each other, they're all going to work together. The upside is that the magnetic field depends upon the enclosed current. It does not depend upon where inside the solenoid I draw that other end, as long as it's inside the solenoid. Which means that the magnetic field should be the same throughout the inside of the solenoid.